welcome to this talk. Thanks for joining in. I would like to tell you about how to optimize the signal-to-noise ratio of a laser scanning microscope with lock-in amplifiers. So let's jump right into it. What are we measuring actually with the laser scanning microscope? For example, this depends highly on the application. For example, in the transmission spectroscopy, we measure the transmission or the absorption. On the SRS or Cars microscopy, so Raman-based microscopy techniques, we measure the pump loss, for example, or the Stokes gain, of course. In multi-photon microscopes, otherwise, we are measuring the intensity, the number of newly generated photons with a higher frequency. And this also depends depends highly on the application. Still, on most of the cases, the setup looks pretty similar. We always have a certain light source, which is depicted somewhere here, which is a laser itself. We have a scanner which scans the sample, and in the end we have the photodetector, which picks up all the generated photos in the depicted way, as could be a spontaneous Raman microscope or a multi-photon microscope. In the end, we have to capture the signal and to record the actual image in this data acquisition part at the very end. And this is the element which we want to focus today. What are the typical effects which we are measuring there? So in the transmission microscopy, we have fairly big effects for example, 10 to the minus 1, 10 to the minus 2 in intensity changes. On nonlinear techniques like Raman techniques, SRS, Cars, or multi-photon, we have often much smaller effects like 10 to the minus 7, 10 to the minus 8, delta I over I, for example. And these effects have to be measured for either on top of the signal, which you can see depicted here on the upper right-hand side, or you have to detect the signal buried very deeply in noise, which is depicted on the lower right-hand side. And still, what we want to achieve is we want to preserve all information content in those signals so that we can measure either smaller signals or measure the same sample even faster. And now let's have a look at a typical setup. We already mentioned the important ingredients, but what are those parts actually? So on the laser side, we have typically on the light source side, we have typically a laser, often even a pulse laser. On the scanner side, we have, for example, galvo mirrors, there's a sample scanner, or a spinning disk scanner, all performing the very same tasks. Now, on the photodetector side, today we want to focus on spectral integrating detectors like photodiode, PMT, or APD, for example. The signal analysis afterwards is always done in a similar way. Either you use an oscilloscope or a digitizer, or, for example, you could also use a lock-in amplifier and the boxcar averager. And what we will see is the impact on the choice which you make can be very big. So, what can you expect in the next 20 minutes? We will show how we can, why a lock-in amplifier can help you to increase the signal-to-noise ratio, how a lock-in amplifier actually works. We will address the question, how can you detect multiple signals with a lock-in amplifier even simultaneously, and in the end, why a boxcar averager can sometimes be even a better choice. But before we do that, let's quickly give you a short overview on Zurich Instruments in our mission. We have a clear mission. We want to provide the best-in-class dynamic signal instruments for advanced R&D labs. And this we do by we take, of course, hardware with adequate speed, high sensitivity, low noise, and so on. This is also what even some of our customers do. But what we add there is what makes the real difference. This is the software. We put efficient software onto the instruments, which allows an efficient workflow, which allows a huge variety of functionality and features, and provides a very intriguing and nice user interface in the APIs. And we even add more value over time. And in the end, we produce there instruments like quantum computing control systems, but mainly, and this is what we will talk about today, lock-in amplifiers, boxcar averagers, and based on that, also impedance analyzers. So now, what is the actual information in the signals which we want to analyze? And this depends on the application. I have on the right-hand side 3 typical cases. And the first time we vary a signal, we have a change in the amplitude for a certain duration. In the second one, we have a sinusoidal modulation, and we can then measure the amplitude of the modulation and the phase. And in the last option, we have even multiple change of multiple parameters, which in the end leads to a mixture of sinusoidals, and we can then measure multiple parameters. Come back to the very later point in time. Now, to understand a little bit more in detail what we actually want to look at, we want to look at the so-called signal-to-noise ratio. The signal-to-noise ratio is kind of the signal which we can measure here, which would be now, for example, here the jump from 0 to 1.5 in this in this case, and we want to compare this to the noise on top of this signal. To maximize the signal-to-noise ratio, it's kind of obvious, yeah. You need to you need to capture all signal components and suppress all noise components which are not relevant. So therefore, the first approach is kind of, okay, we digitize an average. Now, if we digitize an average, this is basically like using a low-pass filter here around more or less DC. And there we see the inherent noise sources, which is first of all the 1 over F noise, which is the inherent detector noise, and which goes then over into the white noise source, and the spikes we see. If we only average and digitize, we capture the part of the signal where we have the highest noise source there, where we have the highest noise, and I would like to show you how this looks like. If we digitize, this is the image which you see on the left hand side. We see first signatures of some beats, which is supposed to be it's a simulated SRS measurement, but it still looks really noisy. Now, if you take the same measurement with a lock-in amplifier in the same measurement time, you get the image on the right hand side. This looks much cleaner, and you see nice clear difference between them, and you don't see this noise. Now, what is required there is the modulation, and so therefore now what you might have seen in addition, there are some additional holes in this image on the right hand side, and this means the information content kind of is different, although I can tell you the measurement was taken simultaneously. Now, why this is, we will get to at the very end. Let's jump now over let's now look how a lock-in amplifier does this. Now, the secret behind a lock-in amplifier is kind of we shift the signal with an additional modulation. So we need to modulate the photon beam and then analyze at that very modulation frequency. And this allows us to shift the analysis on the signal we do into a regime where we have much lower noise than at the DC. On the left hand side, you see a nice comparison of different signals. We choose the same filter, once averaging over DC, then over 500 Hertz, 5 kilohertz, 100 kilohertz. And you can see already a small, in this case, already a small modulation or small modulation frequency can make a huge difference. This is only an example. Now, how does that look for a laser scanning microscope? There you need to do there you need to implement the modulation into a typical setup. If we take the example of a multi-photon microscope we had before, we have a laser and then we add a modulation mechanism right after that before the signal goes into the microscope. The data, the connection later on is taken and combined with a lock-in amplifier and combined with the data from the photodiode. Now, what we have, what we can do in addition is looking at the typical setup of a pump probe microscope, as you would have it, for example, in a car's SRS microscope. So here, the laser has two sources: the probe beam, which goes through in red, and the pump beam. And we only now modulate the pump beam because the pump beam will, together with the Raman interaction, imprint a signal onto this probe beam. Now in the SRS you could do it the other way around. For example, there you would modulate the Stokes beam and imprint, in this case for example, a pump loss onto the signal, and this is what you detect afterwards. Now, how you do that? I list here a few typical modulation methods, so you also see it's not super difficult to implement them. What the modulation method defines is the modulation frequency, the modulation function, for example sinusoidal or rectangular, and therefore defines kind of the achievable signal-to-noise ratio and the measurement speed in the end. Typical principles: the good old chopper wheel, which would give you something like up to a few tens of kilohertz, maybe even 100 if you go push it. Acoustic optic modulators, which have a wide flexibility, electro-optic modulators or pocket cells, or also directly modulated light sources, for example, pulsed lasers. Now, if you choose a certain modulation frequency, of course you have to have the lock-in amplifier which fits that. And here we list kind of the portfolio of us. We distinguish between 3 different lock-in amplifiers, the MFLI going up to 5 MHz, HF2LI up to 50 MHz, and the UHFLI is the one which goes up to 600 MHz. But what is maybe even more important than the pure input bandwidth is the measurement bandwidth, because this defines how fast you can measure. And of course the other elements like having good signal, having a low input noise, and the dynamic reserve. The measurement bandwidth here is, for example, up to 5 MHz on our UHFLI. And of course what is key to be very fast in capturing data in the lab and setting up experiments is that you can have a great tool set in your lock-in amplifiers. For example, you have time domain and frequency domain analysis in parallel. You have the PLL and PID controller, for example, if you want to do resonance tracking, things like that additionally. And of course, you need to have powerful software support. But now let's jump back to the actual experiment. How does a lock-in amplifier work? Why is it, how does it actually, is it able to achieve those high signal-to-noise ratios? So, what the lock-in amplifier does, it takes the modulated signal from your experiment here and multiplies it in the end with a reference signal. So this is the pure modulation signal. This is depicted all in an analog representation, but of course all the task and signal processing is performed in a digital way. After the mixing stage, the low-pass filter kind of filters out all higher frequency components and gives out the amplitude around this reference frequency and the phase. And this filter order is a typical combination of multiple first-order filters. So and therefore forms something like a band-pass filter around the modulation frequency. And in the end, what is important to understand, there are 3 parameters which you have to optimize your system. You have the modulation frequency, you have the time constant, which defines and you have the filter bandwidth and the filter order. Now, if we want to have a short look what the filter bandwidth does and why this is important. So the filter bandwidth is also represented within a time constant, and within this time constant your signal settles to a finite value. And this is important for laser scanning microscopes in particular, because this defines your pixel dwell time up to 1 frequency. And now the idea always must be you want to be as narrow as possible to filter out all the additional noise, and still you want to support all signal components. And on the bottom you see a bandwidth comparison of this. So on the left hand side you see a 50 kilohertz filter, which is pretty noisy still. It has those nice peaks. In the middle you see kind of the best possible choice here. It's a 10 kilohertz filter. The noise is much lower, but the peaks are very well distributed. And on the right hand side you have the 2 kilohertz bandwidth filter, and this filter unfortunately starts averaging out your features in the signal and make your signal to noise ratio even worse, and unfortunately change the shape of your image. And this is what is also clearly visible here. So here I took the same image as before. We set different filter bandwidths here, and you can immediately see, depending on the filter choice, the image clearly changes. On the left hand side you have a slightly noisy image, still it has some nice resolved features. In the center we have a pretty clean image with kind of perfect, going down perfectly to the 0 more or less here between the beats. And on the right hand side, where the filter bandwidth is too narrow, we start smearing the beats, and so the resolution of the image drops, although it looks super clean in terms of signal to noise ratio. So now what you can do in addition is what you can do with modern lock-in amplifier technology in addition is something very famous or very cool. So we can go for a pump probe microscopy, and instead of having 1 pump, we now have 2 pump branches simultaneous. And what we do, we change the normal pump probe microscopy. We add a second pump branch. We add we add a second pump branch depicted here now in blue, and we modulate the first branch at frequency f1 and the second at a different frequency, which is important. It must not be commensurable with the first one. Then we put both into the same lock. We put the photodiode signal into the only one lock-in amplifier, but we feed into the lock-in amplifier both modulation frequencies. Now what a modern lock-in amplifier can do, it can demodulate the probe signal simultaneously at both frequencies, f1 and f2, and therefore capture the two frequencies. Now, what you can imagine, for example, that you perform a SRS microscopy measurement where you have two Stokes pulses, one pulse train tuned to the resonance of PMMA and the other one tuned to the resonance of polystyrene beads. And now we acquire the signal in parallel, and what you can clearly see, you get the two images, you get them simultaneously built up. And now let's have a quick freeze at that image. Now I think you also clearly know what the holes in the PMMA image before were. These were the positions where actually polystyrene beads were located, which you saw, of course, with the digitizer, because you couldn't distinguish between the signal coming from the PMMA branch and the polystyrene branch. If we make a cut now through those images, in this case in the middle, you can see depicted in blue the cross section of those two beads, and depicted in orange the cross section of this bead. And since we cut this a little bit off from the center, it's a little bit more narrow. And so this is what you can do with the modern lock-in amplifier, and you can even drive this further. You can go up to 8 different frequencies if you want, for example, or you can also look at the mixture of multiple frequencies. What is, for example, very in particular interesting if you want to combine pump probe microscopy with AFM cantilever, where you look at the near field excitation. Now, mentioning pump probe measurements in general, we could also imagine something very particular. What you can do, because those measurements are based on very short pulses, and those short pump probe pulse trains can be analyzed kind of, we might want to analyze pulse by pulse, and this is what you can see here. So in case of normal pump probe experiment, you would delay one one branch against the other, and depending on the delay, you would see an imprinted change which the pump pulse imprints onto the coinciding probe pulses. And on the pump pulse train, it would mean you have for example, every second pulse of the probe pulse train carrying a signal. Now, in this case, another instrument comes into the game, the so-called boxcar averager. The boxcar averager does something very similar like a lock-in amplifier, where while a lock-in amplifier takes a sinusoidal reference signal and multiplies the original signal width, the boxcar averager takes a window function with a finite duty cycle which we can define. And there's a very important other aspect. While the lock-in amplifier has kind of a digital RC, has a digital RC filter here at the low pass filter, the boxcar has a normal moving average, and we'll come to in a minute why this is key. Now, how does the analysis of the periodic signal which are not sinusoidal work? So we have a low duty cycle signal, and the signal is confined in a short pulse in time. So the shorter the pulse is in time, the more it is spread out in the frequency domain. And now a lock-in amplifier performs the measurement by capturing only the fundamental harmonic here. The boxcar averager, on the other hand side, measures only during a very short relevant time when the signal is kind of high, and the smaller the duty cycle, the further this spans out in frequency. And so if we make the boxcar window smaller, we extend it in frequency and pick up more signal at higher frequencies. Now, let's get back again to our initial idea of, to our initial concept of probing every second pulse. With the boxcar averager, we have a so-called baseline suppression. And what we can do there is we take the positive boxcar window and put it on the pulses which carry the signal, and we take a negative window which we put over the other pulses. So therefore you see it's very similar to a lock-in amplifier, but we can vary this boxcar window duration and can fit that to the actual signal. And you see there, since we have also, when we subtract every other pulse, we get rid of this DC component and pick up the signal only at the odd harmonics. And this, in combination with the filter function of the lock-in with the boxcar averager, can lead to really great results. Why is this? In a lock-in amplifier, the signal settling is nonlinear. So you have kind of an exponential, nonlinear in the time domain. So you have, for higher filter orders, it takes some time until they kick in. For shorter filters, they rise very quickly, but then take a long time to settle to the final value. And the boxcar averager there has a big benefit sometimes, because the signal settling is now completely linear. So this means there is no correlation to prior data, because you can define the precise number of boxcar windows over which you want to average. And with that, we go to the final example. We have the stimulated Raman scattering microscopy. There we scan over the entire image, and the data was here acquired pixel by pixel. The interaction was pretty small, because there were quite small beats used in this experiment. And what we can in the end actually do is we can compare the pixel dwell time at the same signal to noise ratio. You can compare this on the lower right hand side from those cross sections. So they are very comparable, but for the lock-in amplifier it took 14 milliseconds to take this data, and for the boxcar averager the image was taken twice as fast. With that, I would like to conclude my talk. So what we learned is how to optimize the signal-to-noise ratio with a lock-in amplifier, and why this actually works, mainly also in contrast to a normal digitizer. Remind you of the two top comparisons here. In addition, we went for we looked how the multi-frequency demodulation can work, and how this can be really beneficial for example, for things like SRS microscopy with 2 Stokes branches, because you can capture 2 images simultaneously at the same time with a minimum of interference between them. And also we looked into the working principle of a boxcar averager, and why this can be very beneficial for periodic but non-sinusoidal signals, as you would have them, for example, in pump probe measurements. With that, I would like to thank you for your attention, and finally we also solved the mystery why we have those holes in the image. Now please ask any questions, or just reach out to us anytime. Thank you for watching.